I will present the solution to problem G of BGOpen 2018 Gameworld Tornado. So in this problem you're given as input multiple rectangles and you want to compute their combined area, right? And which is that for this which is the sample input. So how do we do that? Well, we convert each of our rectangles to multiple events. So this is one input rectangle, and we convert it to these two events here. Where each event has an x position, two y positions, and a value. So the first event is +1, the other event is -1. And we do the same with this other rectangle here. And so when we have converted all of our rectangles to events, we sort our events by x value, and then we process them one by one. So if we were to solve this problem naively, this is pretty simple, because what we have is a large array of all of our y coordinates. So, okay, we have 0, 1, 2, 3, 4, and 5, right? And what we do is that, okay, we set all of these values in our array to 0 to start with, and then we process our event. So we process this first event, okay, and we add, okay, we should add 1 here and here, and we should update our x value to the x value of this event, which is 2. Okay, and now we get to the next event, which is this event here. So then we have x prime, our new x value is 3, and before we add this event to our array, we want to compute the area, the total area before from this event to the last event. Okay, so the x difference is x prime minus x times the number of elements in our array which are greater than 1, which in this case is 2. So we see that this area becomes 2, which corresponds to this area, which is correct, right? And now we want to add this event to our array, which we can do easily by updating these two values. So this one becomes 2, and this one becomes 1, and our x value now becomes 3. And we can continue processing our events that way. However, solving the problem this way is unfeasible because we have to check the whole array for each event. And since we can have up to 10 to the 9, our coordinates go from 0 to 10 to the 9, our array has to be that large, and we can have up to 100,000 rectangles, so we need to check our array up to 200,000 times, and it is simply not possible. So we can do it in a better way by using a segment tree. So segment tree is a very nice data structure that lets us update multiple values and real multiple values in log of n time, which is exactly what we need. So in this case, we would construct a segment tree that looks something like this. So this one corresponds to this first part, 0 and 1 and 2, 3, 4 and 5, and these two here become discarded. They are outside of the board, but it doesn't matter for our yes. So what we do is that, okay, when we process this event, right, Okay, well, then we need to add 2 and 3 here. Okay, so then we go in our segment tree and we go down. So now, okay, now 2 and 3 is inside the segment, but it's not entirely contained within it. And we see if we move down here, then it's entirely outside of the segment, so it's uninteresting. But if we move down here, it's still sort of contained within. Here it's totally outside, but here is actually the whole segment. So we add +1 to this node here, since it is the first node which is entirely contained within the segment. And what we do is that we used a little bit smarter segment tree than normal segment tree, because we say that each node also has a score. So the score is either, if the value of a node is 0, which is the case of most of these except this one, and then the score is simply the sum of the score of the children of this node. But if the value of a node is greater than 0, then the score is the size of the segment within this node. So the score of this node would be 2, since the size of it is 2. And that means that the score of this one, since it's the sum of the children, also becomes 2 and 2. And so now we can read out, in fact, the area which is contained by the whole segment tree at the root node very efficiently. So when we now come to this next event, we can simply read out the area contained very quickly by looking at the root node, and then we add this event. Okay, so let's see, it's in fact somewhat contained both here and here. So if we go down here and we see that, okay, this is the first node that is entirely contained within the segment, we add +1 here, and we go down here, node number 4, okay, we add +1 here. So we see that when we go back up and compute the score in this subtree doesn't change, because this node, which contains this one, already has a value greater than 1. So the score doesn't change here, it doesn't look at its children. But in this case, since this one has a value of 0, and now this one gets a score of 1, so this one also gets 1, 1, and we can compute the new sum of the children here, which is 3. So we now see that the new area, which is contained here, or by this line, is actually 3. So let's look at what happens when we get to this corresponding event that corresponds to this one, so this new event. Okay. So we want to process this event. Okay, so it's -1. So we go back down. So in fact, we go back down the exact same way as we did here. And okay, that is this node, but now we do -1. So now the score is 0. But we see that one of the children has a score. Since the value of this one is now 0, we will look at the children to find the score. And since this one has a score of 1, this one has a score, so the new score here will be 1, 1, and the total score here is now 2, which we see also matches here, right? And then we can continue this. And now, so this is a very efficient and nice method of solving this problem. But we have one more problem, is that if our segment tree is to contain the entire range of the coordinates, it will have to be very large, since there can be up to 1 billion, the x values can get up to 1 billion, and same with the y values. So what we do instead is that we do very nice technique, and we call which is called dynamic segment tree. So instead of constructing the entire segment tree on start, we just start with the root node and say, okay, this contains the entire from 0 and all the way to 10 to the 9. And then okay, I need a new I need to add something within this half. Okay, then I construct this node and I construct them as I move down, and this is a very easy way of solving that problem. Another method is to use what's called the index compression, and we create a map because we know the areas of we know all the coordinates of the rectangles beforehand. We know what coordinates are interesting for us to look at, and we can say, okay, position 1 in the segment tree corresponds to coordinate 5 to 100, right? Because we know that there is nothing happening between those coordinates. So that is another method of solving that problem. But I believe that the dynamic segment tree is much easier and much nicer. So all in all, this problem runs at O n log n, which is a very nice running time for this problem.